Okay, folks, here's our last and final video of the week. I'm going to go over, I think the topics are important for the test that you're going to take. I'm going to try to do them in order of importance here. First thing we're going to talk about really quick is that integral almost means area. We know integral and area are the same thing, but it almost means area. For example, if we have a region that's above the x-axis, we'll find the area of this region right here, then the integral from a to b of that function is exactly the area. Okay? Let's go over to this region over here. If I take the integral of this function right here, I'm going to get a negative number because it's under the curve. I might get negative 13. Negative the answered function right here. What it'll do is it'll move both things above the curve. I can do it right from a calculator page. Menu. It's a little, there we go. A little bit out of the light. There we go. Menu, calculus, integral. And I could say from 1 to 3. If I want to make sure it's always positive, I can do the mustache man. Choose the absolute value tool. X squared plus 2x minus 15 dx. And no matter what parts were positive or negative, it'll move them all up and always give me back a positive answer. Okay, so that is integral, almost means area. By the way, oops, sorry about that. That's on page 25. I'll make sure I put that in the notes on this one as we go. So we're going to be skipping around in the packet. So the next thing we're going to talk about is on page 42. It's actually on the next page as well, but I like the page 42 version better. So let's go to there. And it's a problem that I think is probably going to be there. That's why we're going to go over it. And it has to do with something we haven't talked about yet, which is average value of a function. Okay, so we're on page 42. We're going to fill these notes in. Okay, let's say you were a teacher with 25 students in class. You give a quiz. How would you figure out the average score? You'd add up all the scores, right? And then you divide by the number of scores. And so whatever it was for this one, you'd be divided by 25. Please remember that add up in calculus just means integrate. Integrate means add up. So let's apply that to a function. Now let's say you wanted to find the average value for all the points on the curve between a and b. For example, if this height was 7 and this height were 3, there's other heights in there. This one is probably 6.8. This one's probably 6. I want to find all of the heights, add them up, and divide them by the number of heights they have. Well, now, how many points are there between a and b? There's actually an infinite number of points between a and b. It's a problem if we think of it that way, but what's the distance covered between a and b? For example, if this started at 3, if a was 3 and b was 10, distance covered? 10 minus 3, or 7. So the distance covered over that interval is equal to b minus a. So we can sum up all the values of f of x, scrolling up, and then divide them by the difference that they cover, which is and that will give us the average value. So the average value of the function is going to be the integral from a to b of f of x. Remember, that's going to add up all the values of f of x. And then we're going to divide it by the distance between b minus a. Sometimes they write it like this. B minus a. Makes no difference how we write it. It's just you're going to take a function, you're going to integrate it. It's going to tell you, it's going to sum up all the values, and you'll divide by the length of the integral. It really isn't complicated. For example, if they ask you to find, it's going to come up because it's one of the little trick things. It says find the average value of the following function over the defined interval. So what would be the average value between 3 and 6 of x squared? Well, it would be 1 over 6 minus 3, off to the side right here. Okay, so that would be the integral. I know you can't see it there. From 1 over 6 minus 3, that's the length of that region of the integral from 3 to 6 of x squared. So I've changed that to a 1/3. I actually did the physical work to integrate it. You won't have to because you'll have a calculator to do it. And it got a final answer of 207 over 9. That just means for curve, x squared, which looks like that. And I started at 3, and I went up to 6, and I found all the heights in between, added them up. The average one divided by the number of them I had, the average value would be 207 over 9. whatever that's going to be. We set up these next. This makes sense when I set them up. If they want the average value of a function, it just means you're going to integrate that function, because average means sum it up. Sine of x from 0 to 2 over pi dx, because it's going to be calculator version, you're just going to put it in the calculator, multiplied by 1 over 2 pi, because that's 2 pi minus 0. We can put that in our calculator and get an answer out. If we want the average value of this function right here, it's going to be e to the 2x dx from 0 to 5, and the number out there is just 1/5. It's going to be whatever the value is of that piece right there. Now, the question is, why do they use this a lot? They know that you guys are going to mix, why do they use average value a lot? They know you guys are going to mix two things up. There's two things that always gets mixed up, and that is the difference between average value and average slope. Like, I'll guarantee you in whatever question they ask, they're going to ask for both of these things. We don't want to confuse the two. Average slope, or average rate of change, is just the average slope. Average slope is 2 points, it's fib faba. Always, always, always fib faba. Average value is when we're going to integrate. We're going to add things up and put them all together. A lot of times I'll change the word value to score, because when you think of score, you think of tests, and you know in the test you're going to add them all up. Integrate means add them and divide them by the number of things they have. Here's two examples of how the problem could look, which says find the average value for this function between 0 and 3. That's just going to be an integral from 0 to 3 of 2x squared multiplied by 1/3. If they ask for the average slope of a function between 0 and 8, you're actually going to fill the values of the function in and do fib faba on the problem right there. Let me show you the difference. We'll see it more in problems as we go. This is more like an intro to it. The average value of this function, as soon as I hear value, I know it's going to be the integral from sine of x dx from 0 to pi over 2. And that's going to be multiplied by 1 over pi over 2, because it's pi over 2 minus 0, 0. That's going to give me the average value of the function. If it says the average slope, I'm going 2 pi minus pi over 2, sine of 2 pi minus sine pi over 2. I can put that in the calculator and see what answers I get, but those are the difference between average value and average slope. If you flip back for a moment, we're not going to do them all now, to page, getting there, to page 26. I put in a really quick thing about average value into the review packet right here, but you also have it on the other page we just looked at right there. So to combine all these things together, everything combined would be about finding averages and estimates. And if I were to guess what one of the multiple choice problems is going to look like, it's going to look just like this. They're going to give us a set of data, and first thing they're going to ask for, they might ask for something like the average rate of change. Average rate of change is average slope. So for this whole interval, I'm doing fib faba. Fib faba gives me 19 over 60 for that one right there. That's a rate. That's why it's fib faba. If they ask me to estimate the average value of this function, that would mean I would want to integrate from the start of the function 0 to the end of the function 60 of 1 over, and multiply that by 1 over 60. How would we find that value when we have a set of tables? Usually they'll tell you which way to do it. You can usually do it either way. Most likely you can do a Riemann sum approximation. In order to do that, I wouldn't worry about the trapezoid unless they specifically say trapezoid. I'm going to take all the points up here and I'm literally going to plot them all. There's 0.26, 10.40, 20.55, 30.10, 40.60, 50.32, 60.45. If I'm doing a left Riemann sum, I started drawing from the left side, and I figured out the value of each little rectangle and added them all together. So average rate is going to be a slope. Average value is going to be an area under the curve. Sometimes they'll just give you the area. Sometimes they'll give you a function, just tell you to find it. I think what's probably going to happen is they're going to give us a Riemann sum and ask us to figure it out and divide that by the number we have right there. Okay, a lot of stuff, I know. So now let's talk about applications to geometry. In the past, I think we had to worry about this a lot. I don't think we have to worry about it as much because we're going to have it in front of us. right now. We've already talked about area under the curve is the integral. We know some things are positive and some things are negative. Keep that in mind. If we're doing area between two curves, you're going to have your calculator. In order to do area between two curves, you have to do upper minus lower, but you need to know where one starts and where one finishes. All you're going to do is graph and do an intersect tool. And you can find individual areas for this region and individual areas for that region right there. Remember, it's always upper curve minus lower curve. Everything's upper curve minus lower curve. If things are symmetrical already, you can integrate a portion of the symmetric graph to find your answer. Not as important when you have the calculator, but for example, on this curve right here, if they asked me to go from negative A to A, if I just went from 0 to A, I could double the answer and get the correct value on the curve right there. Here is a sphere. If I want the area of the sphere, I could just take this region right here, and I could integrate from 0 to 4 of just that region, then multiply it by 4. Okay, where we're not going to spend a lot of time now, where we would have in the past, is on volumes of rotation. And the reason we're not going to spend too much time on it is, you have the equation. It's going to be with you. It's right here. Remember, the two y's are always upper and lower. And the axis is what you're wrapping around. You're just going to set up an equation, and we'll do this more in review as we get there. If you only have one curve and one axis, throw away the second part. If you have two curves and no axis, throw away the axis. If you just have one curve, throw the axis in the other curve. But volume of rotation are always going to be pi, and then the p squared in there. Now the other part that comes off that, and you notice I'm going through it pretty quick because we're going to have it all in front of us, is conic sections. Sorry, not conic sections, cross sections. The base is always s squared, which is always upper minus lower. And they're going to tell you what the shape is. So we don't really need to go over this that much. We have them all right here. More than likely, they're just going to ask us to set them up. If they tell us whatever shape we have, this constant goes out in front. So if they gave us two curves, if they gave us x squared and square root of x squared minus 1, and they ask to find the trapped between the two, might look something like that. Sorry, if they ask us to find the cross-sectional solid, and the shapes are quarter circles. First, I need to figure out which curve is upper and lower. I really don't have to because it's squared. I could grade, and I know what it is. It's going to be upper minus lower, close parentheses, squared. That's my s squared. Now the question is, where am I going to start and finish? Well, because you have your calculator, you can graph the two, and you can find the intersection points here and here. And you could then graph it. I'm making them up. 0.27, 0.64. And you would then able to find a cross-sectional solid. Be aware of the difference between a cross-section and a volume of rotation is going to be in the words of the problem. If they give you a volume of rotation problem, they're going to tell you something is revolved around an axis. If they tell you it's a cross-section, they're going to say sections cut perpendicular or cross-sections, and the shapes make, I know, moving around a lot, one of the following forms down over here. Okay, we're not going to spend a lot of time on this one because we just finished the topic. I don't even know what's going to be there, but I'm going to go over it really quick anyway. Differential equations, the general rules are separate, integrate. This is page 29, by the way. Separate, integrate, and solve. A quick AP trick, a derivative is a differential if you already have it written down. So, for example, if it says y prime equals x squared plus 2, we would just rewrite that as dy dx equals x squared plus 2 plus 2. Change the y to dy dx. I've only seen this once, and I only saw it on multiple choice. They told me that v sub t is my equation. Velocity is the derivative of displacement, so I could rewrite this differential equation as ds over dt. And then follows, which is integrate and solve. The main one we talked about is for exponential growth and decay, in which the rate of change is directly proportional to the quantity. So to pdt equals kp. The steps are all listed here. We've gone over it enough, but in the end we get the piece kitty answer, p equals ce to the kt. If it doesn't ask for steps, don't even bother doing them. And remember, they're going to give us conditions like at t equals 0, p equals 400, and at t equals 10, p equals 1000. We can fill the information in already because I have an initial condition. I already know that C is equal to 400. So I use that to solve for C. Then if I substitute in, to find, next I'm going to find K. If I'm substituting in, I'll do the next problem here, which is 1,000 equals 400 e to the K times 10. And if I'm solving for K, I can often just do it in one step. You can think about it like this. K is going to be equal to, I'm going to get everything else over to the other side. So I'm starting with 1,000. I'm going to divide by 400. I'm going to LM both sides to make the E go away. And then I'm going to divide by 10. The reason I wrote this down here is so that you don't have to bother trying to figure it out during the test. If they give us a proportional thing, whatever the initial condition is, that gives you C. And whatever the other point is, this is the quick way to find the other piece of the problem right there. So if I were to flip over, there are a couple of other types. I don't really think I need to go over this next page. It's just a specific example of what I showed really quick. So you have a model of the problem there. We just want to make sure we know about Peace-Kitten problems, which is when we have things are proportional. The rate of change of something is proportional to the difference of two things. Okay. When we go to fill in those problems, there's a couple of them written down here. It doesn't make a difference what they are. Whatever is the bigger number always goes first. And then when we write out the problem, we'll end up with what's known as the Peace-Kitten. P to the KE plus N, where N is a constant that's going to be added on. No matter what this is, negative or positive, the constant that's always added on is that number right there. And then what will happen is the C you will get, the C, will be the difference between the number you started out with and this difference at the end right here. So if you add these two numbers together, you'll get your initial condition in the problem. Oop, I'll do that again because I just showed that, but I didn't highlight any of it. Coming down the bottom of these two problems, I'm going to grab another color marker just so I can go over it again. So here we had a constant of 32 subtracted off. And if I scroll down the problem, I have an initial condition at t equals 0, a is 98. The number in the problem, 32, will always be the number that's on the end of the problem right there. For example, in the second problem, I subtracted 130 off of the problem, so it's adding on 130 there. If you look at whatever your initial condition is, at t0 it's 98, the C value, the C and the N will add up to make exactly what you started out with. So even if you take a look here in the second problem, the initial condition was 98. If I take the 130 and I add on the negative 32, I'll get back to the 98 that I had. So we have those things written down right here, so you can see them as you're going. You'll have models of the problems. There are other types of differentials. I have 4 models here. These are the most standard 4 models that you'll see. You can look them over on your own. I'm not going to go into them in detail, other than when you start with the problem, you're going to separate, integrate, and solve. This is always it's always easiest when the cross products just give you the P's and DP's on one side and K's and DT's on the other side. When that doesn't happen, like on the next problem, if you cross multiply over 1, you'll get dp equals kp squared. Anytime you have a degree other than 1, you just bring it to the other side and put it to the negative power, or divide by that power right there, and you end up solving it out. Sometimes they're connected to the inverse proportion of things like square roots, or such as here. But what I'm going to let you know is all of these problems can be solved in your calculator using the differential equation tool. Let me turn this on. If I go to menu, Put that where we can see it. Put it right there. Calculus. Differential equation solver. I'm going to put this equation in right here. I think I can put it in just like that. Let's try this. Let's see what happens. I'm going to pause it for a second, make sure. Hold on. Okay, so the format you might calculate a little different, but it'll be totally acceptable. So they asked me to solve equation, which is p equals k over p to the 1/2. When I put it in the calculator, instead of using dp dt, I have to write it as p prime. That's just the shortcut for that. Equals k over p to the 1/2. You put in your independent variable, which is t, your dependent variable, which is p, and it will have solved that equation out for you right there. If you want p by itself, and you notice they solve without giving me p by itself, watch this. You can go to here and go menu, algebra, solve. Oops, that's not solve. Algebra solve. I can grab this equation, put a comma, and just put p. Hit enter, and there's p by itself. And it's long as one. They may give you more than one answer. You can choose. Usually, the first one is just fine, and you'll have an answer solved out from there. So, differential equations, even if they give them to you, you're going to solve them in the calculator. We'll practice it on the ones that I've seen coming up on the test. Okay, we talked about solving differentials. There's more in there. We're not going to go over those right now, but you can look through them if you need to. But you'll have these in front of you so you can see them as examples. Really quick, slope fields. Just going to spend a couple seconds on it. Keep things separate. Remember, if things change in the x direction, you're going to look to see how things are affecting things in the slope field. When you're sketching a slope field, all you're going to do is find values for dy dx using different x's and y's. I've never seen them usually they ask for 4 points. I've never seen them ask for more than 6 points. Remember, if the bottom of your fraction is 0, you're going to get a line straight up and down. If the top of your fraction is 0, you're going to get a line flat. If you get 0 over 0 as a fraction, you put no line on there. There's no line that goes on the graph. And when you're graphing slope fields, 45 is slope of 1. Negative 45 is the slope of another. Don't go crazy trying to make it perfect. They're not looking for perfect. Remember, when you're looking to check to see if a field matches on this function right here, y is on the bottom, so it's going to do the opposite of what y says. So it's indirect. So as y gets bigger, x should get smaller. Y gets bigger, x should get smaller. Here, as x gets bigger, y should get bigger. Here it gets bigger. Slope increases. But the question is why this value is negative. Here's why. You just look at the sign. That's right there. And I always work in quadrant 1. It's just easier because x and y are put here. So if x and y are positive, the answer is always going to be negative. And it's going to go there. So those are the general things. I have one more thing to go over. Promise that's it for today. Really quick, everything's going to come down to some basic stuff. It really is going to be, they're going to be looking at limits. Limit from the left equals limit from the right. They're going to look at derivatives. They're going to be looking at slopes and rate of change. Remember, slopes, instantaneous slopes are about the same as average slopes, fib-faba. Integral is going to be area under the curve, which is approximately the number of boxes, or we'll probably end up doing left Riemann sums. That's going to be their big one they look at. And the things we're going to need to remember the most are the equation for local linear line, which we have right here. That fib-faba is approximately the instantaneous slope. If you integrate rates, you get quantities. And if you derivate quantities, you end up getting rates. And those are our key topics. That's the general review. I have one more topic I missed the other day I'm going to put in here. I'm going to pause right now and go to that, and then we'll be done for break. Okay, this last topic is one we didn't talk about because it only kind of shows up on the AP. I think they're going to give it here for you, but we have these notes. It's on page 45 to show you how to do the problem. You could write the definite integral as what's called the limit of a Riemann sum. It just means that if I took an integral and I turned everything into rectangles, the distance I'm covering is b minus a. The area of under the curve here would be equal to the summation, the adding up, of all of the rectangles I had, where f of x is the height, and this dx is the distance right here. and it's just equal to however much distance I've covered, a lot of words here, divided by however many rectangles I had. So for example, if I started at 1 and went to 21, the dx, the width of each rectangle, is going to be 20, because that's the distance I covered, divided by how many rectangles I had. So if I had 1, 2, 3, 4, 5, 6, 7 rectangles, let's change this. Let's make this 15. So if the distance I was 14, and the number of rectangles I had, that tells me each rectangle is going to be 2 units long. In order to get exactly right, the number of rectangles has to be a number of them. So what they do with this problem is they turn it from a question about a certain number of rectangles and normal eyes and lengths. I'll explain where they all came from in a little bit. That the area of curve exactly limit as approaches infinity. That means you have an infinite number of rectangles. That means that this number is going to be infinity, and this number is going to be infinity. This little thing is just a thing that moves me from one point to the next, to the next. All the AP wants to do is translate from either an equation form to this form, or from this form to an equation form. We're not even going to get into the details of how that all works, other than to know the number of rectangles, if I add them all up, is approximately equal to the area under the curve using integrals. I'm going to flip to the next page and just show you how we translate from one to the other. In order to translate, we have to get it into this form right here. And the best is you're going to have your document with you while you're working. Okay. So A is your starting number, 2. B minus A is the distance from the end to the start, where the 5 came from, for right there. Dx is going to be B minus A over N, where the N stays, so that's why it's 5 over N right there. And Xi, the part we're going to fill into the equation, the part that's going to go in here, is going to be these numbers, A plus B minus A I over N. So for this problem right here, A is -2, plus B minus A was 5, the letter I, over N. Once I have those values, all I'm going to do is fill them into the equation. I'm going to rewrite limit as n approaches infinity, from 1 to infinity. I'm going to take the equation 1 minus 5x squared, and I'm going to write 1 minus 5, whatever this piece is, squared, I'm just filling it in, and at the end is the dx, it's just the 5 over n. That's how you work that problem on in there. I'm not even going to go over any more of these problems right here. You're going to have this model. We'll see if they give us one that's enough. I haven't seen them as a free response question, so I don't want to go crazy on it yet. But all this is, remember, just a way of taking a function and writing it as a limit of Riemann sum. And the same thing in the end, when we're ready to, we can go backwards well. But we have a model for it right here where all our numbers come from, and we'll be able to see how to set them up back into the equation right there. Okay, that's it for this week. I will talk to you on Monday. Take care.